All right, hello everybody. This is not like a required lecture or anything. This is just a quick review on pointer arithmetic. Because when we do recursion on things like arrays or vectors or strings, sometimes it'll be more convenient to do it in terms of pointers rather than like sort of manipulating the thing itself here. So if you need a quick refresher on pointer arithmetic, this is the place to be. So let's say we have like a couple of pointer variables, right? So we've got an int pointer p and an int pointer q. What do these things mean here, right? Like, is it legal to do stuff like p plus 1 or q minus 1 or to compare like p less than q or q minus p or stuff like that? When are those allowed and what do those mean? Well, in order to sort of see what those mean, we need to sort of look at like the way things are placed on the stack here like this. So for normal stack variables here, there's no guarantees about how they will be placed in memory. So let's say that we've got three sort of ints here like this, right? So ints, at least on like, Intel processors on the operating system we're working on here, ints have size 4. So if you were to ask what is the size of an int, size of is like a built-in operator that tells you how much memory a thing takes up, it would reply that the size of int was 4 there. So even though these variables are like together in my program, right, I just sort of put them like that, they may not be right one after another in memory. Like the compiler is allowed to sort of put other stuff in between them, so there might be gaps in between them there in memory there like that. So there might be like, something else between x and y and something else between y and z there. Even if they are together, they might not be placed in the exact same order here. So they might be placed in the order y, then x, then z. Note that these are spaced 4 apart here because, again, ints have a size of 4. So that's where they're sort of spaced out like that. It's even possible that one or more of these may not exist in memory at all. The CPU has some internal storage locations called registers that are the fastest place to store information. So if y doesn't need to be in memory, if we never like take a pointer to y or anything that requires its address, the compiler may have put y into a register, which means it's not in memory at all there like that. So for just normal variables, you can't make any assumptions about what their addresses will be. If you try to do any kind of like pointer arithmetic on sort of separate variables here, you get either undefined behavior or in some cases what's called unspecified behavior. So for example, if p is a pointer to x, right, and q is a pointer to y, if I do p plus 1, that might take me anywhere. Like it's not necessarily just going to be like, oh, the next int variable or something like that, right? Same thing is true for q minus 1. If I go, what's 1 int before y, that might not be x. That might be some other random thing there like that. Or the order of these two might have swapped, right? It might be that y actually comes first in memory and then x is sort of later there like that. Similarly, if we compare addresses, we're not comparing values. We're not asking is 2 less than -4. If I say p less than q, I'm comparing addresses. This is asking, does p live earlier in memory than q? The answer might be true or false. It could change every time your program runs. Like each time your program runs, the system might decide to put x and y in a different order there. And then if you do q minus y, again, like we're not doing -4 minus 2. The answer to this is not 6. This is subtracting addresses. So what it is doing is it asking how far apart is it from where q points to where p points. Or like you can think of it as like how far apart in memory are x and y there. And that could be anything. Like that could change like while your program is running, like, well, not while your program is running, right? But each time you run your program, the compiler, the system might decide to put x and y in different locations. So q minus p is not some like predictable thing there like that. One thing to sort of note, this is a note down here, right? With pointers, like p plus 1 doesn't literally mean the address plus 1. The 1 is going to get multiplied by the size of an int. So it's going to actually do like the address plus 4 there. Like there's no way that with pointer arithmetic you can end up like, halfway through an int or something like that. So with normal variables, like there's no guarantees, right? If you manipulate the addresses directly, you're in sort of like undefined land. An undefined behavior is really bad because in C++ it means anything can happen. Like there's no guardrails. You're off the map here like that. So maybe nothing happens. Maybe your program crashes. Maybe your program crashes later, like someplace that's completely unrelated to that part of the code there. Maybe your program prints the wrong answer. Maybe it prints the right answer some of the time, but then it prints the wrong answer some other times. Maybe your computer crashes. Computer, like that. That's unlikely, but it is theoretically possible. Like when you sort of write to that location beyond the where a variable doesn't exist there like that. Maybe you're writing to some memory location that controls like whether your computer boots up or something like that right there. All your files might get deleted. Again, that's unlikely, but it is theoretically possible. Maybe it emails your browser history to like the entire class or something like that. Like all of these are theoretically possible. UB is bad because it means you don't know what happens. It might change every time your program runs there. Now, where can you safely do pointer arithmetic? You could do it on arrays or things that are like arrays there. Because with an array, as we sort of saw in the linked list lecture, right, the elements of an array are guaranteed to be placed one after another in memory. So that means if I have an array like this, where I have 5, -2, 1, and 7, the -2 is guaranteed to come 1 int's worth of memory after 5. The 1 is guaranteed to come after the -2, and the 7 is guaranteed to come after the 1. There's no gaps, there's no extra sort of space, there's no reordering in here. So if you know the address of the beginning of the array, like 1000 or whatever that is like that right there, you can easily figure out the addresses of all the other things in the array here. So if you have pointers into an array, then all the things that we said before are bad are actually valid and well defined. If P points to array 0, then P plus 1 just points to the next int's worth of memory, which is the -2 there at 1004. If Q points at the end, right, if Q points here at 1012, like that, then Q minus 1 is just go 1 int earlier in memory and gets me to the value that's sort of before it there like that. If you ask, is P less than Q, the answer to that is true. Now, note what P less than Q is doing here, right? When I say P less than Q, I am not asking, is 5 less than 7? That's not what we're sort of asking here. What we are asking is 1000, the address in P, less than 1012, the address in Q. That is what P less than Q is really asking. It's saying, is the place where P points earlier in the array than the place where Q points there like that. Similarly, you can subtract, right? You can do 1012 minus 1000. That's automatically going to get divided by the size of an int. So that Q minus P basically tells you how many ints back do you have to go to get from Q to P there. You can also do this on a vector or on a string because both of those have arrays in the background. So you can use the dot data operation to get to the sort of underlying like character array for a string like that. So s dot data, if s is hello, that's s sub 0, which is the address of the h. And then if you have a vector containing these values here, right, like that, v dot data, that gives you v0, like that right there. Not p, that is v, like that right there, right? So then v0 plus 2, that's the address of v0, is go forward to 1, 2. That gets you to the sort of 7, the -7 that is in there like that. So the dot data on a string or an array is basically like the backing array that is behind the scenes there. Because pointer arithmetic is well defined in arrays, it gives you another way to loop over an array without using the indexes. So here we've got this array, right? Like that, right? So P equals array. So that means P is pointing to the first address of the array there like that. This array there is the same as if you had asked for the address of subscript 0 there. Our termination condition is when P is at array plus 4. Now, the array has 4 elements, but if the first one is 0, the second one is 1, the third one is 2, and the third one is 3, array index 4 is beyond the end. So I don't actually want to access array index 4 here, but it's fine to sort of ask, is p equal to that or not there? And then when I increment p, again, that's going to move p forward by 1 int worth of memory here. So here we're making p equal to the beginning of the array. P not equal to array 4 checks to see if p has gone beyond the end of the array here. So our array has 4 elements. Array plus 3 is the last element. That's the 7. The 3 is there. And then the 4 would be 1 beyond the end there. Now, if I had p equals array plus 4, like that right there, right? And then I did star p, that would be bad, because now I would be accessing this memory that doesn't belong to me there. But as long as I don't do that, as long as I don't dereference it, and as long as I just ask questions of like, oh, is p equal to array plus 4? That's fine. You are allowed to construct a 1 past the end pointer. You're just not allowed to dereference it here. I was going to write that in green. So p equals array plus 4. That is fine. So like it's valid to construct and compare with a 1 past the end pointer, but we're not allowed to dereference it. And then of course, incrementing p is the same as doing p plus 1, but under the hood that is actually adding 4 to the address, because 4 is the size of an int. It sort of knows how big the pointer points to and will automatically like add the appropriate amount there like that. Now, we could do the same thing with recursion, right? Like we can print with recursion here. So to do this, I'm going to get a pointer to the beginning of the array and a pointer to the end of the array here. Now, note that this end here is 1 past the end. It's really common in C++ that when we say the end of something, we don't actually mean the last element of it. We mean 1 past the end here. So that end pointer is going to be set up to point over here to 1 past the end of the array here. So ARR here, that is a pointer to the first element. ARR plus 4, that is a pointer to 1 past the end here. 0, 1, 2, 3, and then 4 is over there like that. This function is tail recursive. So we print start, we print 5, and then we recursively add 1 to start, which moves start over to the next element there. Given pointers like p and q into an array, here's the things that we're sort of like allowed to do and what they mean, right? P plus 1 means the next array element. P minus 1 means the previous array element. P plus n moves me n elements ahead, skip ahead by n like that, right? P less than q is true if p points to an array element earlier than q. Like if you were comparing array indexes, we're not comparing values. And then q minus p is the distance between p and q. Again, think of subtracting array indexes instead of like values in the array there. These are only valid if p and q point to elements of an array, and of course they have to be in the same array. If p points to one array and q points to a different array, then all bets are off. You don't know how like different arrays are placed in memory there. So we'll use some of this in some of our like recursion on vectors, recursion on strings, some sorting stuff there. So this is just a quick review in case you needed a refresher on how pointer arithmetic works. Thanks a lot for your time, everybody, and I'll see you around.